questions that you would like me to go over? So you were supposed to do review 7 through 11, wasn't that what it was? 7 through 11? You were supposed to do review 7 through 11. Are there any questions on a particular reaction? Those are just going to get better by practice, 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 practice. Yes, it says a solution of ammonium thiocyanate. So ammonium is NH4, and I'm going to separate it because all ammoniums are soluble. And thiocyanate is SCN negative. Reacts with a solution of iron 3, so Fe plus 3, plus chloride. You're right at complexation. Remember, iron is a thing that likes to do complexation, and thiocyanate does as well. So you're going to say Fe, SCN, what's the number? 6. And it'll be 3 minus. The ammonium and the chloride cancel out. You'll need to put a 6 in front of thiocyanate. By the way, this is one, you might make a quick note, one of those memory things. This is blood red. When you make this particular reaction, the product is blood red. Just a very deep, deep red. Good? 9C. Ethanol and formic acid, or methanoic acid. All right, what's ethanol? Well, it has an A, ethanol. If you see F, do you have the Sigma card? Yes, I do. I was saving it because I was supposed to give it to her. There it is. I knew it was in. Yes. Yes. Because she wasn't in. Ethanol is got 2 carbons. My elephant plays basketball, so it's going to have a C2. And the anol means it's got an OH group. Don't get that confused with like a hydroxide, like sodium hydroxide. So that is CCOH. You can draw it structurally if you don't know the formula. Plus methanoic acid. What does meth mean? How many carbons? So it's going to be C, double bond O, OH. And if it's only got 1 carbon, that makes this a hydrogen. What are you going to make? Ideas? All right. Oftentimes, you're going to make water. What's going to happen here is this OH group, one of these OH groups, is going to essentially break off and then take away this H group. Right? This is one hopefully they're not going to give you. It's going to make C, C, O, C, like this, you see. What happens is if the water breaks off, if you take away this S, then this O gets connected to this carbon. So it's CCOC, double bond O. And then you'll have H's for whatever is required. You'll have an H here, 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 here. Notice I'm doing it completely structurally. I think that's called that's an aldehyde, I believe. Good? That's a tough one, I think. I don't think this year they're going to give that to, they're not going to give you a hard one. That's kind of one of those choice, when they used to have choice on them. But that's a good tough one. Any other ones that you'd like me to dive into? On 9G. Phosphorus 5 oxytrichloride is added to water. All right, phosphorus 5, that means its charge is like +5. It's got oxygen and it's got chlorine 3 times, right? Basically, it's POCl3. And it's reacted with water. This is a non-metal oxide, isn't it? But it's got chloride in it too, so it's kind of weird, right? So it should be an acidic deal. Boy, 1985, that was a tough one. I don't know the answer to this one. I would guess it's phosphoric acid, and maybe hydrochloric acid as well, which this would need to be dissociated. I think you'd make them both. But you're going to get the phosphorus. The phosphorus needs to be in there somewhere. So I think you're going to make both of these things. And the hydrochloric acid needs to be split, of course, because it is a strong acid. Okay? Other questions on these? There's tons of them, 10, 11. No? Let's do one more. Let's just pick one randomly. How about 11H? This is probably more realistic. Solutions of tripotassium phosphate. Now, they don't call it tripotassium phosphate anymore. They just call it potassium phosphate. So this will be, well, potassium, it's a solution of potassium phosphate. Forget the fact that it's tri, because it dissociates. Reacts with zinc nitrate, Zn2 positive plus nitrate. Again, I dissociate. All nitrates are soluble, and all potassiums are soft. Potassium is like is a Na in the nacolnoso, and then no is nitrate. So what do I make? This is a very, I would expect this. This would be one question I think was going to, you're going to see one like this. It's going to be zinc phosphate, Zn3, PO4, 2. The potassium and the nitrate are spectators, and they fall out. So you'll need to have 3 zincs and 2 phosphates. If I was to be a predictor, okay, guys, I think what you're going to have, you've got three reactions. This is the first year where everyone's required. They're going to have a redox reaction of some variety. That's going to memorize those rules. They're going to have a precipitation reaction. That's what this one is right here. And then the third one, you know, I don't know. I think you get at least 2. But if I was probably one of those oxide ones, a metal oxide plus water makes a base, and non-metal oxide plus water makes an acid. Or if you take a salt containing oxygen, break it apart, it makes a metal oxide and a non-metal oxide. And if you take a non-metal oxide plus a metal oxide, it'll make the salt containing oxygen. I'm going to guess those are your 3. If I was to put money on it. They're probably not going to have a weird one like this, although it's kind of a oxyacid kind of a thing going on. Okay? Now, today's big topic that we're going to just kind of race through, and actually it came a fortunate day that we cut short on time, is thermodynamics is I think one of the easier things that we learned about. I think this is chapter 16 in your textbook, and I believe chapter 16 truly is the easiest chapter in the textbook. Now, what do you need to know about thermodynamics? There are sort of 2 kind of pieces to the puzzle. Okay, you need to understand the meanings of the signs of our 3 things. So delta H, delta S, and delta G. You've got to know if it's positive or negative, what that means. If you do not know this, you're basically hosed on these questions. And it's easy to get them backwards, isn't it? All right, if delta H is positive, it is endothermic. That means energy is absorbed, right? If delta H is negative, it is exothermic, and that means energy is released. If delta S is positive, this is, of course, actually, let's do one more thing. What is delta H also called? Enthalpy. What is delta S also called? Entropy. And delta G is Gibbs free energy. You don't have to say necessarily the Gibbs part, or just free energy. All right, so if delta S is positive, what word would you put here? Disorder. Don't get that backwards. If you do, you're in trouble. And if it's negative, it is order, right? Delta G, Gibbs free energy. If it is positive, it is non-spontaneous. And if it is negative, it is spontaneous. The other thing to know about this, you should know, is which processes are favored. Exothermic and disorder. Right? And this actually relates to a particular equation. And what is the most important equation in thermodynamics? delta G equals delta H minus T delta S. So you can predict the sign, and there's a sort of a second table we want to look at. Using that equation, all right, we can also some predictions about delta H, and so let's say delta H, again, it's a similar table, delta S and delta G. All right, we have this could be positive, and this could be positive. What will delta G be? You're utilizing our cool equation. Delta G is delta H minus T delta S. What will be the sign of delta G? Sometimes it will be locked into being one particular variety of sign, and sometimes it will be a different sign, or it can be one sign or the other. So if delta H is positive and delta S is positive, what happens? Yeah, but you can say it will be spontaneous at what variety of temperature? At high temperatures. Because if you think about it, if delta H here is positive and you subtract a bigger number, then that will make delta G negative, which will make it spontaneous. Right? What about if it's negative, negative? Except in this case, yeah, it's spontaneous at low temperatures. I should say T on these. Got it? And then if I get, we're opposites, positive, negative, it will never be spontaneous or not spontaneous. And if it's negative, positive, it is always spontaneous. Right? Good? Now, that's kind of the big conceptual pieces. Actually, another couple things on conceptual things before we jump into something else I just thought. If I have a reaction, say, NH4HS, that's a solid, and that dissociates into NH3 plus H2S, and both of these are gases, I want you to predict the sign of delta H and delta S. We're not talking numerical. I'm talking about positive or negative. Delta S is positive. How do you know that, Eric? You're going from a solid to two gases, aren't you? And you're going to a more disordered state, right? So if you're a more disordered state, gases are much more disordered than solids, and so that's how you do it. What about delta H? Yeah, this one may not be known, but you're breaking something apart. Do you see that? I'm not sure you'd know this for certain, but it most likely is also positive because you are breaking it apart. Okay, now this is a positive one, right? So is this one always spontaneous, never spontaneous, or sometimes spontaneous? Sometimes spontaneous. We could figure out at what temperature that it would be spontaneous at. All right? Because if you use the equation delta G equals delta H minus T delta S, what will be true when delta G is equal to 0? We would say that's a position at what? Equilibrium, right? And so if this is equal to 0, you can say 0 is delta H minus T delta S, or if you solve, you can say delta H is equal to delta S, or if you divide both sides, you can say T is equal to delta H over delta S. So if I knew delta H, the numerical value now, we're talking about values in a minute, delta H and delta S, I could divide them beside each other and I could find the temperature. That would be the temperature at which this reaction would be spontaneous. Above which it would be spontaneous or below. I had to think about it. This is the higher the temperature, the more spontaneous. Yeah, the higher the temperature. No, the higher the temperature, the more spontaneous this is. Above this temperature, it's spontaneous. Below this temperature, it's not spontaneous. Good? Is that making some sense? All right. Now, let's do some mathematical stuff. Let's discuss the math, okay? How do you calculate delta H? The answer is there are 4 answers. If you recall, how do I calculate delta H? Okay, the first one is calorimetry. This is actually where it all came from. Calorimetry, you're going to remember the units on delta H are kilojoules per mole. So you need to find the moles, find the kilojoules, and divide them. To find the kilojoules, you're going to use a fancy equation. Not a fancy at all. The equation we've seen quite a bit. Q is equal to mc delta T. You're going to have something to catch or collect the heat. Usually we use water. So you have a container where we're going to heat up or cool down water. The moles probably just from some gram data, and then you solve it. And then you always got to figure out, we did a big lab on this, you have to figure out if it's positive or negative based upon whether it releases or absorbs energy. Calorimetry, second way, is Hess's law. I'll call it version 1. Don't ever call that on the test. That's another teacher that I used to teach with called it that. I think it's easier to think it this way. That's the sum of the products minus the sum of the reactants. That's the easy method. Everybody loves that method, don't they? Because it's the easiest one. The third one is also Hess's law, version 2, if you will, and that's where you're going to add reactions. So take reaction 1. If you flip it, you multiply it by -1. If you don't flip it, you leave it. If you double it, then you double it. All that stuff. And then the fourth one is bond energies, and we just got done with that not too long ago. We waited a while done. That's going to be bonds broken minus bonds formed. Which way are they going to ask you to do it on the test? I have no idea. I've seen all 4 methods, and sometimes the same 2 of the methods in the same year. You just don't know. By the way, the bonds broken are reactants, and the bonds formed are products. Okay, so it's kind of weird that the other one's products minus reactants, and this one is reactants minus products. Remember what we did is we had how many bonds are the single bonds, the double bonds, and you count up the total number of single bonds, and CC single bonds, and CH single bonds, and C double bond O's, and you add them all up, and then you subtract. It's an accounting nightmare is what it really turns out to be, and so that can be an issue. But it is not terribly difficult. It's just a pain. All right, how about calculating the other thing? How do you calculate delta S? Delta S, probably you can products minus reactants works. Products minus reactants, and then oftentimes you're just going to use delta G equals delta H minus T delta S, and you can solve for delta S if you know G and H, or maybe they're going to ask you to solve for H or G, or usually it's G, but sometimes it be something different. Now, a couple of notes about this equation that's easy to forget. The units on delta H in the back of the books are typically given in kilojoules per mole. The units on delta S are given typically in joules per Kelvin mole. So it is imperative that you cannot subtract $50 minus 50 cents and say you got no money, right? You got $49.50, don't you? You must work in the same variety of a unit, okay? So 50 minus 50 is not equal to 0 if you don't have the same, unless it's the same units, right? So you must convert your joules per Kelvin mole into kilojoules per mole, or you can convert your kilojoules per mole into joules per mole. It makes no difference. I prefer to work in kilojoules. So usually this is going to be like, so if I find my delta H, let's just pick a number, I find it's negative 125 kilojoules per mole. And let's say it's we're going to do an experiment at 25 degrees C, and I find delta S to be 210 joules per Kelvin mole. I'm going to subtract what? Yeah, I got to convert T to Kelvin, so that's 298 times 0.210, right? Because then it becomes, because to get from joules to kilojoules, there's 1,000 joules into kilojoule, and then you would just take, on my computer or calculator or whatever, negative 125 minus 298 times 0.21, and I get negative 187 kilojoules per mole, or whatever. Does that make sense? All right, another thing that I oftentimes see as sort of mistakes in this, that you can get confused with the different varieties of delta H's. There's the delta H F0. That's the heat of formation of a particular compound. So if I've got, let's say, of CH4, all right, this would be the amount of energy it takes to form CH4. All right, actually, and that has a reaction. The reaction would be C plus 2H2. Carbon is a solid, hydrogen is a gas, and that makes CH4 gas. And how much energy that takes, that's called the heat of formation. What would be the heat of formation of the carbon and the hydrogen? They're 0. If you have an element in its standard state, meaning the state of matter you would find it in this room at 25 degrees Celsius in 1 atmosphere, which isn't exactly this room, but we call it good enough, then it will always be 0. And they're going to expect that you know that. Okay? So if you have a complex reaction, let's say that we have a reaction like, C5H12 plus O2, and it makes CO2 plus H2O. To balance that, you'll put a 5 in front of the carbon, you'll put a 6 in front of the hydrogen, and that gives me 10, 5 times 2, 10 oxygens there, plus 6, so 10 and 6 is 16, so it'd have to have 8 oxygens. All right, one thing I oftentimes see students do is I say, what is the delta HF0 of C5H12 if the heat of combustion of pentane, this is pentane, is, I'm going to make up a number, negative 1,300 kilojoules per mole. What am I asking for? I'm trying to find the individual delta H for the C5H12. A lot of students say, well, that's the pentane, it's negative 1,300. Now, what you would need to know is the value for carbon dioxide and water. I'm going to stick my head out and think this is negative 242, and this one is, somebody get your, their book, flip to the back of your book and find that table. What's the value for CO2? I don't have that in my head. If you burn pentane, 242 is the reasonable number. Carbon dioxide would be 394. Okay, negative, right? So what I'm asking for is, what is the value for this? This is what gets confusing. Some students think I'm asking you for the overall value, products minus reactants. I'm trying to find one of the components in products minus reactants. So you would say negative 1,300 is equal to, I'll write it here, I think, negative 1,300 would be equal to 6 times negative 242 plus 5 times negative 394. I'm going to round. On the AP exam may not be a good idea. Minus X. Because the oxygen is 0, isn't it? And this is only a 1X. There's no number in front of the carbon, or the pentane, I should say. And then just basically solve for X. We don't necessarily need to do that right now, but you get the kind of idea, don't you? Make sure you don't get trapped into, read the question carefully. This is easy to make the mistake, is when they give you this question, are they asking for the overall heat of the reaction, or sometimes called the heat of combustion if you're burning something, or are they asking for an individual number? If they're asking for the 0F, right, the delta H F0, this means 298 in 1 atmospheres. If they're asking for this, then that's when you need to solve for the individual value as opposed to the global value. You don't want to get kind of sucked into that, because it could just be, you'd go, oh man, you'd look at that and say, it wasn't that hard and I blew it, and you don't want to do that. Good? Hopefully you have somebody sitting next to you who has a Barron's book. So turn to page 522 in the Barron's book. What's that? Okay. Hey guys, we're going to do, it actually starts, it's question number 2 at the bottom of page 522, and it goes on to page 523. It says, write the separate balanced formation reactions for each of the following. So what would be the formation reaction for sodium carbonate? You would do this, 2Na solid plus carbon solid, plus oxygen makes Na2CO3. Now, what do I do with the oxygen? How many oxygens do I need? 3 is incorrect. I need 3/2. And when you do formation reactions, they're going to be so that you make only 1 mole of this. So you do need to work with fractions oftentimes. So see if you can now do the other 4. HCl, H2O, CO2, and NaCl. NaCl is a little tricky. See if you can all do that. What were the other chemicals? I forget now. HCl. So for HCl, you'd say H2 plus Cl2 makes HCl. And you would put a 1/2 in front of each of these, right? And then for the water, you'd say H2 plus 1/2 O2 makes H2O. And then for the sodium or carbon dioxide, C plus O2 makes CO2. You only got to watch for these ones that have got Cl2s or whatever. And you got Na plus 1/2 Cl2 makes NaCl. So that's the answer to A. All right. Calculate the enthalpy change for the reaction. All right, they gave us a big reaction. How are we going to do this? Part B. They've kind of given it away by question A. What method are we finding using delta H? The add reactions method. Or, we might do products minus reactants. They give, oh yeah, I think we might be able to do it. Our reaction is Na2CO3 plus 2HCl makes 2 waters plus carbon dioxide plus NaCl, 2 of them. Now, do we know the numbers? The table is on the previous page, 522. So what do we know? All right, so the sodium carbonate, they did give me the heat of formation of sodium carbonate. So this is a negative 1131. The HCl is negative 92.5. The water is negative 242. This is negative 394, I believe. And the salt, I do not know, but negative 413. What method are you going to use? Products minus reactants. Everybody do it. .42 or 46? 146. That'll be in kilojoules per mole. So to do the products minus reactants for delta S, it's the same deal, isn't it? They've already gave us the numbers. It's just a little different kind of a variety. The carbon dioxide is 214. I'm going to round. 214. I'll put it in green here. The water is 189. The NaCl is 72, right? HCl is 187. And the sodium carbonate is 136. One thing you'll notice is very rarely, typically delta or S values are given without a, they're all positive. They're not negative. So you'll take 189 plus 214 plus 2 times 72 minus 136 plus 2 times 187. Yeah. Negative 146 and 38. what's the temperature at this one in D? Is it 298? 300 Kelvin, you mean? 300 degrees Celsius? This would be 673. That's quite hot. 573, thank you. Times 0.038. Yeah, because it's 38. And it was positive. One was negative and one was positive. All right. That's not too bad, is it? That's the first part. I don't know. I didn't check the second part. Let me check it, though. Oh, yeah. What's the value of the equilibrium constant? What's the equation? Actually, we should definitely write that. I'm glad they asked that question. It's an important one. What is the equation for equilibrium constant as it relates to delta G? Delta G equals negative RT natural log K. What's delta G? That's delta G. Actually, this brings up another important point, okay? All right, 168 negative. I got to remember that. Okay. The second part of delta, all right, we're going to say, what's delta G's value? Negative what? Negative 168. Watch carefully. What am I going to do? 1,000 joules per mole is equal to negative 8.3145. That's R, right? That's in joules, because this is in joules per Kelvin mole. R, and then T is 600 and, or 500, I keep thinking it's 600, 573, right? Times K, natural log of K. In my solver, I'm just going to take negative 168, double or triple zero, plus, parentheses, 8.3145 times 573 times natural log of X. X equals. Just solve for X using your solver. So get your solver out and see if you can figure out what this. I get 2.06 times 10 to the 15th. But what's the mistake you're going to make? You're going to forget to convert this to joules because this is in joules. Don't forget that. In the thermodynamic world, there's always these little changes. Why didn't they just put them all in the same units? I don't know. I don't know. Wish they did. Don't make no sense to me. But that's just kind of things we got to know. Okay? Let's see if we can throw up another question. Thermodynamic one. I don't want to use ones. How many thermal questions do I have on here? 12 and 13 and 14 and 15 and all right, let's discuss the labs then. What type of a might they ask you into thermodynamics? It's going to be a calorimetry experiment. So the thermal lab question is the lab you did. And we kind of almost did it twice, I think. Did we guys? Yeah, we did the candle, didn't we? Out of oil. Yeah. The oil candle. So you kind of had, that was my invention, but that's basically the gist of it, guys, is if you have a reaction, so sketch this here. If you've got some kind of a reaction, and you're going to place in here the reactants. Let's say a classic one would be hydrochloric acid. This is the one they did about 5 years ago. You took magnesium, you dropped it in hydrochloric acid. What's the value of delta H? How would you calculate it based upon an experiment that you would do? What would you do? What is delta H? This is always start with the math, even though you don't have any numbers, okay? They're not going to give you a calculator at this stage. They're not going to say calculate it. They're going to say explain how you do it. You see, it's kind of a different. What is delta H units on? Kilojoules per mole. So you've got to find these two numbers. Once you know the kilojoules and the moles, you'll take the kilojoules and you divide it by the moles. That's as simple as that. Now, if I take these two things together and I pour them into each other, what do I need to know? What measurements do I need to know? The mass of HCl, the mass of magnesium, or whatever. It could be the mass of any, pick up a chemical. Any reaction you've seen in your entire chemistry life is fair game. They're probably going to do simple ones, though. They're not going to. This one isn't quite simple. What's going to happen when you dump the magnesium in the hydrochloric acids? Well, true. We can write the reaction. Magnesium plus hydrochloric acid is going to make magnesium chloride into GCl2, right? Plus hydrogen gas. But it's going to produce a gas, right? That's going to be a gas. But if we're talking thermodynamics, what are we actually going to need to really care about here? The energy. So what's going to be obviously changing when you dump these guys together? The temperature. You're going to have the T at the beginning, or initial, we would say, and the T final. Temperature will either rise or fall. It's going to get hot or cold. In this case, it would get hot. We did this very experiment. So it starts at 20 degrees. If you want to make up a number, I think it's not a bad idea. It's going to go to 24 degrees. Oh, delta T is 4 degrees. Because how am I going to find the kilojoules? Yeah, MC delta T. The change in temperature, maybe 4 degrees or whatever. The mass is the mass of either the magnesium or the hydrochloric acid. It's actually the one that is the limiting reactant, the one that you run out of first. In this case, they almost always choose magnesium to be the limiting reactant. So this would be the mass, and the specific heat is the specific heat of the chemical that was warmed up. Okay? The chemical that warmed up was hydrochloric acid, but hydrochloric acid, of course, is a solution where water is the solvent. So the specific heat of a hydrochloric acid solution would most likely be 4.18, or very, very close to it. Maybe it's 4.19 or 4.17, but it's going to be awfully close to 4.18. We almost always heat up water. So if you found that, you could plug it into here, right? And then the moles, how would you find the moles? You would know the mass of magnesium. Let's say you had 1 gram of this. You could convert that to moles, couldn't you, quite easily? Just using the periodic table and the fact that magnesium has a molar mass of 24 grams per mole. You take the two numbers and divide, and then here's the mistake that a lot of people will make. You'll get a number, but the actual value is going to be, in this case, negative because it got hot. The negative sign is never found out by mathematics. It's found out by logic. Does that make sense? That's kind of an important little caveat you want to watch. Make sure you figure that out. Okay? And then they're going to ask error questions. All right? Always ask an error question. There's always one error question. What is the biggest source error in this experiment? The energy is lost to something other than the hydrochloric acid. Right? So what effect does that have on the value of delta H that you would calculate? Could make it high, low, or have no effect. And explain. Actually, and this is a good point. When we say higher or lower, usually in thermodynamics, when we mean higher, we mean the actual absolute value is higher or lower. Because actually it's going to make it lower. Right? Because we observed a 4-degree temperature change. For example, and you may want to make up a number. Say, assuming, you can write this. Let's assume that it started at 20.0 degrees and went into 24.0 degrees. Okay? Then that's what you observed. But if you indeed could have captured all the heat, it would have gone to 25 or something, right? So therefore, the number that you calculated is lower than what it should be in terms of an absolute value. Technically, it's higher because it's a negative delta H, if you think about it. And I would probably talk about it in terms of absolute, and then I might make a note. I'm speaking of absolutes as opposed to, the negative, because it will make it lower if you think about it from the negative perspective, the opposite, positive and negative numbers. I don't know if I'm being clear, but good. This invariably is your thermodynamic question. If they ask a lab question, there will be one lab question. Which topic are they going to pick this year? I don't know. I have to look back. I don't remember what the lab question was last year. I'm trying to remember which one it was. I don't think it was thermo. Okay? Questions on that? Does that make sense? That is a good place to